Welcome, everybody. This is Dr. John here for Extract Talks. Today, we're going to be talking about one of the most exciting topics known to mankind and womankind, because we're going to be talking about research. I love it. I love research, R&D. That's what we're going to talk about today. Welcome, everybody. We're going to be talking about research and development and equipment, specifically supercritical CO2 equipment that is used for research. And we're going to be talking about some of the systems there, specifically our M2.5. It's like we made the M2.5 how many years ago, and we never talk about it. And then people start calling us, and all of a sudden it gets momentum, and we start selling them, and it's pretty good. Now it's going to be a big seller for us. Huge hit.
A lot of R&D applications, but let's not forget the universities.
The universities,
exactly.
Been
a huge portion of our inquiries.
Right. Let's kind of talk about that. But before we get started, I always got to give the invite to everybody before I forget. You can indeed subscribe to our channel. And when you do that, and you push the little bell button, it'll give you like ding, it'll show up in your feed. And you're like, oh, we have yet another podcast. So that's a good way to know if we have new, fresh content out there. We're trying to post every week. So that'll give you an idea as to what we can do for you. And if you ever get a chance, you should just give us a call. If not anything, just to say hi. We'd love that, wouldn't we?
We're chatters.
Heck yeah.
Guilty.
We're talkers.
Yes.
We're talkers as charged. Yeah, if you get a chance to go ahead and push the subscribe button, push the little button that says the little bell, you'll get your idea there. And now we're going to talk about the 2.5. Here we go. 2.5, what is it? Go.
Benchtop extractor.
Extractor.
That's the short of it.
That's right.
It's bigger, it's better, it's got a lot more options than pretty much all the other ones I've seen out there. But
bigger, better, faster, stronger. We're R&D guys. We kind of made this for our own purposes. This is an R&Der's R&D machine. Yeah, in terms of more options, you're going to get all the options, and you're going to put that on steroids, and then you're going to get more options, and then on top of the options, you're going to have options.
Yeah.
We customize these machines specifically for your research project. And what we found out a long time ago was that process equipment is just not like one size fits all. Whether you're doing something, you got to kind of change it around. One of the things that's really helpful, especially when you're talking about CO2, is that you can have a manufacturer who's going to really customize that machine for you, tailor it for your particular desire. And then if you need to tailor it even more later on, just give us a call.
Yep. Took the words right out of my mouth. It's in general, the premise is customized solutions for a very specific application. And it ends up being, again, square peg, round hole, the type of thing. If you have just a standardized piece of equipment, you may be doing R&D or product development, and the standardized equipment doesn't necessarily accomplish what you want. And then the conclusion is, that equipment doesn't work. Well, yeah, our basic premise is, we need to develop and actually engineer the solution for your processes. And that's where all these options come from.
Okay, that's a really awesome point. Yeah. How many times do you think that you've had a graduate student or an undergrad go and try to get something to work? They come back to you, say it doesn't work. And you're like, I don't have time to go in there and actually find out why it is that it doesn't work. Oftentimes you're trying to do something with your process or trying to get a certain result that you're looking for, but you're not able to do that because the equipment won't allow you to do that. And you really have to be able to modify that equipment to understand or measure the phenomenon that you're trying to measure, right? It's just like one size just does not fit all.
True. I'll answer your question though.
Yeah,
what's that? The answer is three graduate students in the last 3 weeks.
Three.
They may or may not be from Quebec.
Cool.
May not be from Quebec.
I see. So we're going to get a whole bunch of them coming our way, because there's kind of, once people start talking, they start talking to each other. Small systems, they just generally like, oh, hey, I can use it for that. I can use it for that. Let's talk about something about along the lines of sustainability. That's the other thing that we really think a lot about here at our company. Basically, all of organic chemistry, all of chemistry, maybe chemical engineering, is geared towards petrochemicals and petrochemical research. You use the solvents and you put those solvents together, and you're doing that research under a petrochemical auspice. Okay, if you want to do sustainable research, most research laboratories, most teaching laboratories, most teaching curricula do not have the tools or the infrastructure to do any of that kind of research at all, period.
Yet, they are the company's highest on the ESG score.
Well, that's true. That's true. Or they all desire to do it.
Yeah.
They desire to do it, but at the same time, they don't have the infrastructure for it. They're like, okay, well, how are we going to do some sustainable or green research? I know. We'll turn off the lights before we leave. We'll buy a eco-friendly heater that has just the same amount of heating and with 0.5 watts less, something along those lines. Okay. And if you really want to get to the point where you're changing a lot of the petrochemical based research, you really need to have the infrastructure there. And that is almost non-existent at every major teaching university on the face of the planet. I would say that there are very, very few exceptions, but that's just the case. And if you think about it, when you start a chemical process, you're talking about chemical hazardous waste. Usually it's always incinerated, going off as greenhouse gas, or HAP, which is hazardous air pollutants, with no good. If you're talking about solid output, you're talking about hazardous waste then going into a landfill. And then you're teaching the kids or the graduate students, how to do it in that way without even teaching alternative means of research.
It's almost like reinventing the wheel, because we've gone far down this path of, like you said, petrochemical.
Yeah, and it's supported by all the petrochemical industries. 100%.
It's the quote unquote gold standard of just these processes. It literally is a new, costly, and it's a huge paradigm shift that is needed.
Right. Think about this though. If there is no adaptive technology to cause the paradigm shift available, there will be no paradigm shift. And the people who always did it one way, they spend an entire career with millions of research dollars formulating and buttressing their way they're doing things. 100%. There is no way to change it, and then they're teaching the next generation and the next generation and the next generation how to do that. It's perpetuated. And that is the modern day university laboratory kind of industrial complex, if you will.
Standard, yeah.
Yeah, and it's basically purely unsustainable. And there are some small number of innovative colleges that call us and say, oh, well, we don't want to be teaching our kids how to do, for example, 100% synthesis with all of these chemicals. Why don't we do them in a more green solvent, right? That's the future.
Yeah.
And it's not only the future from the standpoint of sustainability, it's also the future from the standpoint of cost.
Cost, I was just going to say.
100%.
Usually a lot of times you hear, well, hey, this is environmentally sound or friendly, and it's going to cost you 10x the investment, but you should do it because it's environmentally sound and you want to do the right thing. Rarely is it cost effective to do it the way that best suits the planet and everyone.
Yeah, and
this is one of those cases.
Yeah, this is one of those cases where you not only have the benefit of having a low cost way of doing things, but you also have the benefit of it. Hey, you're not creating all that hazardous air pollutant. You're not creating all of the solid waste, hazardous waste. You're not also creating the next generation of know-how without the benefit of having exposure to, hey, you need to be doing things maybe in a more sustainable way. That's the thing. You have research upon research upon research upon research. It's all based on petrochemicals with very little sustainability brought into the research, and it just starts to perpetuate itself. That's why, in order to have a paradigm shift in the way people operate and to get to a lower cost basis in the future, there has to be research on these more sustainable methods. Reactions, for example, in supercritical fluids or fluids that can be recovered, fluids that don't have HAP in them, fluids or things like that. And is it for everyone? Is it for everything? No, but the infrastructure doesn't even exist to try it.
Right.
And the people who are yelling most on the sustainability side are also the people who are training everybody to be unsustainable.
Well said.
So that's a problem. We are going to really try to change this paradigm, and that is by mass customization for the research community of this platform technology that we have, which is called the M2.5, and it can be used as a reactor. For reactors, you can have a stirrer on the reactor. It has all kinds of ways you can put detectors on it. You can fill it up with fluids that are sustainable. You can mix the fluids with sustainable and unsustainable fluids too. That's actually a sustainability play. Instead of using a liter of material, you're using 50 milliliters of material, and the rest of it being sustainable fluid.
Right. I don't know if we've clearly said this thus far. Our there are many supercritical fluids that
Right.
you could possibly use. Our engineering, our processes, we focus on supercritical CO2. Of
Right.
course, it can,
Or water, CO2.
or water. Yeah. There's a lot of different options out there, but the comparisons we're making with sustainability and off-gassing and greenhouse gas production, we are mainly speaking and comparing between supercritical CO2 as a solvent versus
A non-polar solvent or polar solvent, a product solvent, whatever, right?
ethanol, hydrocarbons,
Yeah,
et cetera.
specifically those, yeah.
Which are the gold standard
Right.
of botanical extractions, for
Right.
example.
Right. There's these companies now who are using refrigerants for doing type of thing. So those are if they want to use a forever chemical that you can't ever measure and use that in your reaction, well, that might work for some particular things. I mean, if you can recover that at 100%, which you can't, but that may be somewhat sustainable too. But then you'd have emissions associated with those refrigerant. It doesn't really work out very well for Scope 1 type emissions. But yeah, essentially, like ethanol and hexane and all these, and these typical hydrocarbon solvents that people are using for synthetic work, for extraction work, for separations work. Those are all the things that we're talking about.
Yep.
And the chemistry labs around the world are pumping out hundreds of thousands of gallons of those, or hundreds of thousands of liters, millions of liters, in fact, of very pollutive type stuff, and that's all being incinerated. Most all of it is being incinerated, or there may be some innovative trying to do some like recapture in energy,
sequestration,
something like that,
some sort. Yeah,
but then probably not in the flue gas. You're still talking about CO2 being generated there. It's not only CO2 though. It's if you're talking about a refrigerant or something like that, liquefied. You're talking now about what do you do with that?
Is that R134?
Yeah, R134. There's hundreds of different refrigerants.
Is Freon in there?
Freon would be another refrigerant that you could use. But those are perchlorinated or perfluorinated materials. Those are known to be harmful to the environment. They're known, and people use them as accelerants, obviously, like in hairspray and stuff like that. But you don't really eat hairspray, right? For a food, it's probably not very good.
Speak for yourself, sir.
Yeah, I just every morning. All right. So yeah, those are the types of things. Anyway, let's get into the features and let's get into the different aspects of the M2.5.
Sure. The base model for our benchtop extractor is a 2.5 liter ASME pressure vessels. Go all the way up to 5,000 PSI, depending on your the material load capacities, dependent on your product density. It's very commonly used by our customers that have much larger industrial scale operations. They're using an extractor like this, a 2.5 liter, for their own experimentation and their own product developments. They're tinkering with, speaking of another feature, potentially a co-solvent on there as well. It's a beefed up version of a lot of the benchtop extractors that you'll find out there.
Yeah, versatility is the key there. You got high pressure. You're able to basically pressurize the vessel at high pressure. You can do high pressure reactions if you want to in that vessel. You can do a co-solvent where you would do liquid-liquid exchange. If you need to do some extractions of solid materials, you're looking to get either some volatiles out of the solid materials. Say you're trying to dewater something or dry it. That would be another good way. You can do that sustainably. Sterilization is another thing that you can do with this system, along with standardized extractions. So, and we've done a lot of different customizations. We have a pump that feeds into an extractor. We can have more than one extractor on there. We can have we can have a large one. We just sold one with a 20 liter on it, for example, as a standalone. It has our M2.5 as a 2.5 liter vessel on it. But if you need to have something like a 20 liter vessel, we can just sell that as a separate unit. And they were going to use that for liquid extractions. For example, you have the larger vessel would be filled up halfway with a liquid, and you'd want to exchange out the material into CO2 using a liquid extraction type of technique. It's kind of cool, very innovative.
For the base model, there's a 2.5 liter extraction vessel, 2.5 liter collection vessel, and a 2.5 liter recycler as the base unit. And then all these other features we'll get into, but yeah.
We've done some things like, for example, where we've done controlled pressures. So you can control the pressure, like a pressure gradient. You can also control the release of the CO2 and pressure at a certain rate or at a lower rate. One of the issues with CO2 is that if you depressurize too quickly, you're going to possibly cool everything down to the point where the CO2 will sublime it'll go from a gas to a solid. That's a sublimation. You want to try to prevent that. You want to reduce the rate of venting. That we had one recently where that was a key thing that they wanted to do. The other thing would be detections. You can put detectors on there. UV-Vis,
FTIR.
Yeah, near infrared, and things like that. We can put those in line. You can put them after the extractor, for example, if you want to see what's coming off. You can put them in any number of places in the system. You can tell us where you want and we'll plumb it in. And then those are fiber optic flow sensors. I think they're stable up to like 3,200, 3,000 PSI, something like that. Those are pretty good. Usually we don't put those upstream of the back pressure regulator that you need to have on the system just because you don't want to break
the detector.
The detector, okay. Yeah. That would be one thing.
C1D2.
C1D2, yeah.
That
for those of you
recent request from a prospect.
Right. If you are in an industrial setting and you have a need to reduce or eliminate or control the amount of flammable liquids that you'd have in a system, then you definitely need to have a C1D2 or a C1D1 certified system, which means that we pressurize the whole entire cabinet and we make it ready to go in that type of environment.
We assume everyone knows what that means. Class 1 Division 1 or Class 1 Division 2 just has to do with fire, NFPA?
Yeah. So the key thing,
acronym.
The NFPA, National Fire Protection Association.
They regulate how much, flammable or explosive solvents and storage and treatment.
Right.
In a facility.
In this case, like for example, if you have this unit, okay, you put the 5 to 10% of materials inside of the CO2, it's not flammable. Up to something like 30%, it's not flammable. That's something to keep in mind. Also, in terms of the C1D2 environment, that would really depend on what you're putting into the system. Suppose you call us up and say, hey, what I really want is a CO2 butane system. Okay, then we have to figure out something because there might be a leak from the butane, and then that would require that the room be designed for that particular system. We have this thing is pretty small. You can actually roll it into a walk-in hood, or you can actually put it into a hood if you want to.
Right.
If that's something that's of concern for you, you want to do some sort of reactions or something like that, we can put it into a hood, and that way you can keep it from causing problems. And then the actual cabinet itself is pressurized. It's always blowing fluid, blowing air out, that there's no way for the explosive stuff to go back in and hit the electronics and go kaboom.
The lovely thing I want to make clear is that the base unit, as we're describing it, doesn't require any facility. There is no class and no division where our equipment needs to go. It can go right in your lab or in your production facility, anywhere really.
Right. There's a UL standard for laboratories, and that's the one that this one is compliant for. So overall, the unit, just to describe it then, it's a system that is comprised typically of two pumps, one being a solvent gradient and then the other being a CO2 pump. The CO2 pump really provides CO2 to the extractor column. The extractor column is 2.5 liters typically. And after the extractor column, you'd have a back pressure regulator. The back pressure regulator is manual. And then as a fluid goes through the back pressure regulator, it goes into a collector. That's where you can collect your product. If you have flow going through your extraction vessel, it'll go through that back pressure regulator and precipitate out at lower pressure in your collector product. And then we also have a recycler on that system too, that you don't have to use much CO2. You can just fill it up, use it, recycle it, and then you can outgas it from there. If you're interested in recovering that CO2, there's also CO2 recovery systems where you can re-liquefy. That should be something that could be of interest to you, especially for larger institutions. If you guys are looking to, for example, have cryogenic delivery of high pressure liquid CO2 to a particular location for research purposes, and then you want to collect the flue gas and then recondense it, you can do that. You just have to collect it, put the flue gas through a pipe and put it out into a compressor and chill it down. We make all of those systems that would be available for that, including the CO2 distribution, the CO2 pumping, the CO2 filling systems, the actual extractor itself, and then customized economy type recovery of CO2 for reuse if you need it.
For a lot of botanical processors that have greenhouses or growing facilities, recovering and redistributing CO2 into the grow facility. That's another popular one.
Right. When you're talking about research and development, I think the key really is to have a versatile machine. That means that you should be able to go a wide range of pressure, wide range of temperature, flow or without flow, with and without co-solvent. You should be able to control the pressure either manually or automatically, because that is a thermodynamic parameter, obviously temperature and pressure. And you should be able to increase the vessel size if you need to, if you're going to do some liquid-liquid extractions or something like that. Or if you need to do some reactions, and you can use the pumps and all of the fluids that would go into that. Yeah, there's a lot of versatility there. And then if you need to have detection, you can do different detectors on it. Really, the sky's the limit in terms of being able to really make a system that's going to work for your research.
Mm-hmm.
Yeah.
Yeah, your vessel size point there reminded me of another, actually, vessel swapping.
Yeah.
Different vessels, whether it's the same size or different sizes. We've also done that for customers, where you can basically have an additional vessel or 2 or 3 carts that you
different
just
skid
put over. Yeah, exactly. A lot of flexibility.
Lot of flexibility. Yeah, those are the main things with the M2.5. And I think it's really important that for you researchers out there who are really concerned about doing things in a sustainable way, I would encourage you to look at the sustainability of what you're currently doing, whether it's from a chemical engineering standpoint or a chemistry processing standpoint, and start to say, well, hey, look, if I don't even have the infrastructure to be more sustainable, to reduce the environmental footprint, maybe it'd be a good idea to start thinking about how to get that done. And this actual system would be a really great way for you to start, because it gives you what you need, and it also has a lot of versatility built into it. There is no other companies out there that are going to go to the level of customization that we will. There just isn't. Before we get off here, we should also highlight a couple other type, like we've sold these to nutraceutical companies, right? Yeah.
Medical device
companies, also polymer companies, sold them to extrusion companies. Why is that? Well, they're looking to clean up their additives. Okay, you can remove volatiles, you can remove aromas from different items. All polymers, polymer beads, they have what's called extractables and leachables. For critical clean applications, that's a really important application where you, for example, you're trying to understand, is my polymer going to leach out the particular process aid that we have made it in, whether it's a porous material or something like that? Well, you got to get that out. In order to get it out, you really have to have a lot of fluidity, and you can't use like another solvent, because you're just replacing what you're trying to get out with a solvent. Then the solvent's stuck in there and leaching out into your body. And critical clean applications, specifically for medical device manufacturers, that's a really good application for cleaning up polymers. The other thing is sterilization research, or even sterilization of hard materials. Those are some other things, even botanical materials.
I was going to say spices, yes.
Yeah. Or like tissue scaffolds and things like that. So like, for example, if you need to have sterile like bone tissue scaffolding, we actually talked to some people who were planning for that, right? With that, thank you so much for joining us. Again, this is Dr. John and Connor. We are here to answer your questions. Please give us a buzz. We'd love to talk to you about your research application. We'd love to customize a system for you to be in the vanguard of your next medical device. And we're willing to customize these machines tailored for your need. Thanks a lot, and you guys take care. Bye now.